So let's take a look at some hints for your Unit 2 exam. I've done my best to try to make the review sheet, and from the review sheet I made this PowerPoint presentation, but please know that I may not have hit everything. So one of the things I know on your review sheet is what is the origin of the word atom, and the answer is going to be Greek. It comes from the Greek language. I know it also then comes from Latin after Greek, but I think Greek's the right answer there. We'll be talking more about this coming up. There are some questions about the pieces that make up an atom, and we talked about electrons and protons and neutrons in what we call the nucleus. So kind of have a sense of that. Of course, electrons are in a cloud outside the nucleus. Kind of know a little bit about this. Electrons are negatively charged. They're basically massless. Protons are positively charged. They weigh about 1 U. Number of protons is equal to the atomic number. They're positively charged. Neutrons also weigh about the same as protons, and they're also in the nucleus, and they're neutrally charged, and they help the protons to coexist. So kind of know generally that. There's a question or a couple questions, I'm not sure, about these different models of the atom, and of course this is today what we know about an atom, so kind of know a little bit about these. For instance, what's the difference about Dalton's model, Thomson's model, Rutherford's model, Bohr, and Schrodinger. Let's see. We talked about the electron in a cloud outside the nucleus. So here's the nucleus, and electron is in a cloud outside of here. But electrons will be at different energy levels. And in that sense, I think there's a word on your test called quantized. And for instance, this elevation, as we climb the steps, our elevation is quantized versus as we go up a ramp, it's not quantized. So in the same way, we say the energy associated with electrons are at discrete energy levels. One of the things we talked about, if this isn't drawn to scale, so please know that, but if this is the nucleus, and of course we have electron, this looks like since it's got just one proton in the nucleus, that must be hydrogen, and here's the one electron around the hydrogen atom. If it's in what we call its ground state here, okay, and can you see where what's being shown here is energy is zapping it, and the electron is moving up to a higher energy level. So we say energy is absorbed to do that. Now what that can actually create are these what we call what do I call them here? Spectrum. And this is what we call a dark line spectrum. So each of those blanks is where an electron has taken that specific energy to be promoted to a higher energy level. Let's see, over here we have something a little bit different. In this case, notice that the electron is in its excited state, and as it falls back down into its ground state, energy actually is released, and that gives us what we call these bright line spectra. And one of the reasons I wanted to talk about spectra was that when we talk about stars, these are different spectra of stars, and you can see here is the temperature of the star, and it's like a fingerprint. The two things that these spectra, these lines of what electrons are transitioning, basically, in this case dark line spectrum, so energy must be absorbed, these must be absorption spectra. The two things that they show us are what elements are present on distant stars. Is that not awesome or what? And they also tell us the temperature of the star. So those two things. I think there's a question maybe about fireworks, and fireworks actually where the electron is falling from an excited state down to its ground state, and it's emitting that light, and that's what's happening to create that pretty fireworks. All right, Heisenberg's uncertainty principle. There's a question on the test, and I think it goes, the crux of it is something like this. Uncertainty means I just don't know, right? Well, the thing that we're applying the Heisenberg's uncertainty principle to, it applies to very small things. And in this case, we're talking about electrons. And it says you cannot know both the location and energy of a given electron. You can't know them both. You can know one or the other, but you can't know both of them. Heisenberg's uncertainty principle. Part 2, I talked about the periodic table. There is a question on there about the law of chemical periodicity. Well, hopefully you see in the word periodicity the periodic table. So if something is periodic, and I kind of talked about days of the week are periodic, you go through each of the 7 days and then it wraps back around so that your Sundays line up, your Mondays line up, Wednesdays, Thursdays, Fridays, Saturdays. Okay, that is days of the month are periodic in that sense. So that's what we mean about the law of periodicity. It repeats itself. Okay. You're going to want to know groups. Groups are, these are groups. Groups go up and down. Groups are sometimes called families. We are family. Okay. And then on your periodic table, remember my favorite way to talk about the groups are in terms of A. Then we have A over here, and then these guys are B's. Specifically 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. So and then B's are here, and these are also B's. So periods go across like this, okay, and I can see I don't have, this should be 7 here. So period 1, period 2, period 3, 4, 5, 6, period 7. Okay, so we would say what? For instance, potassium and selenium are in the same period, period 4. Now, why do we have this periodicity law going on with regard to the elements? And as they line up, they actually have the same number of valence electrons. That's what makes them behave similarly. And remember, we said you can get valence electrons for the group A elements just by looking at the group numbers. So we have 1 valence electron, 2, 3, 4, 5, 6, 7, 8 valence electrons. Let's see, what did I want to mention here? Well, you've got some questions. I think the reason I have this one maybe because the JAG. Okay, remember the JAG separates what? These are metals and these are non-metals. I think that might be it. You're going to want to know some group names or some family names. So for instance, 1A is the alkali metals, 2A is the alkaline earth metals, 7A is the halogens, 8A is the noble gases. Okay, the A's are all main group elements. Your textbook calls them representative elements. These mean the same thing. And then these B guys are the transition elements. These purple guys are the intertransition elements. Sometimes these guys are called the lanthanides, and these guys are called the actinides. So know those. The most abundant element in the universe is hydrogen. The most abundant element in Earth's crust is oxygen. The most abundant element in the human body, now this kind of grosses me out to take a human body and break it down to different elements, but that's what it is, oxygen. Talked about the concept of an isotope, and remember with an isotope what happens is they are atoms that have the same number of protons, so they must be the same element, but they differ by the number of neutrons. Where it goes, differ by the number of neutrons. Okay, so if they differ by the number of neutrons, then a few things. One is that they're going to have a different mass number, because we said the mass number is a counted number, and you literally look into the nucleus of an atom and you count number of protons, which is got to be because it's a particular element, plus the number of neutrons, which actually can vary. And then we said that you can talk about different isotopes by just giving the mass number. So if you see something U-235, uranium-235, this is the mass number. So this is the number of protons plus the number of neutrons. And we did some examples of, you can go ahead and look on the periodic table to look at the atomic number for uranium, and that's protons, and you could subtract that number from 235 to get the number of neutrons. Remember how that works? Ions, we said an ion is where you have a different number of electrons than you do protons in the nucleus. If it's neutral, they're going to be equal, so electrons and protons will be equal. Then we talked about metals. We said that metals tend to lose electrons, and as they lose electrons, they become positively charged, and they're called cations. We said that nonmetals tend to gain electrons, and as doing so, they become negatively charged, and we call those anions. And then on your periodic tables, I had you put what? +1 for 1A, +2 for 2A, +3 for 3A. And then over here with 7A, I had put you -1. I had you put -2 for 6A, and I had put you -3 for 5A. And then up here, these are the charges that those atoms of those elements, or those elements, will form. So you're going to want to be able to do this, where this is the excuse me, the symbol of the element, and then we have the charge. If there's nothing up there, remember it's neutral. In the upper left hand corner, we have the mass number, so that'll be the bigger the two numbers. In the lower left hand corner, we have the atomic number. So we did this example where, notice I know it's neutral because there's no charge up there. So this number right here is the atomic number. That's the number of protons. This guy right here is the mass number, so that's the number of protons plus the number of neutrons. Okay, so this is what we came up with. Be able to answer those questions. All right. And then we talked about there are two types of compounds. There are molecular compounds and ionic compounds. With regard to molecular compounds, we call them the repeating unit of molecule. Ionic compounds, we call the repeating unit of formula unit. We said that if you have a metal in your formula, then you're like 99.5% sure you've got an ionic compound. If there is no metals, if you have all nonmetals, then you have a molecular compound. And then we said consider hydrogen a nonmetal for purposes of this class. And then talked a little bit about ionic versus covalent chemical bonds. So let's see, a covalent chemical bond was electrons are shared between two atoms. Ionic chemical bond, electron is transferred to make a cation and an anion, and then they'll attach together. We talked about electronegativity, and that's this Greek letter looking like X, and that's the tug of war. That's to know the one with the higher electronegativity. It's funny because this is electronegativity and it's the Greek letter chi. So this is the high chi. The higher chi then actually is going to win in the tug of war, and so it will it'll not win in the tug of war. It'll be, the electrons will be more pulled in that direction with the high electronegativities. We use Pauling scales for electronegativities. Remember I said that electronegativity will increase across the period, and I said the electronegativity will increase going up. And that's the same thing as it decreases going down. Same diff. And then this whole tug of war thing, if we have a tug of war and actually the electronegativities are the same. Remember, deltas mean change in. So if you go ahead and look at one electronegativity minus the other electronegativity and you get 0, that's what we call a nonpolar bond. If you go ahead and do the difference and you have 0.5, that means that it is polar. So that's, remember, you'll have a partially polar, partially positive, and partially negative part. The partially negative one is the one with a higher electronegativity. From there, we go to polar and then strongly polar. So all of these, like this says, are where electrons are shared, a covalent bond. And I went ahead, and this will be different for different chemists or different textbooks, but I went ahead and said if the electronegativity difference is 1.7 or greater, then electrons entirely going to be transferred, and it's going to be leave you with then something that is negatively charged. I'll put let's see, I'll put Z, negatively charged, and something that's positive. The thing that gave up an electron is going to be positively charged. So something like that. The electron is transferred to make a cation anion. A relatively straightforward calculation is to calculate how much a compound weighs. Now, units are going to be AMUs or U's, okay? And so basically all you got to do is add up all the decimal numbers. You add up decimal numbers. So for instance, the example I think we looked at for water, you take 2 times the decimal number for hydrogen plus 1 times the decimal number for oxygen, and that's how much a water molecule would weigh in atomic mass units or U's. This is what I call crisscross, where you're going to come up with binary. Binary means 2, so you're basically going to take a cation and an anion, and you're going to write a neutral formula unit. Okay. And then the next thing you need to be able to do is to name the ionic compound. The name of the metal will just see, the first name will be the name of the metal, and I don't think I have any. I think it will be 1A, 2A, or 3A metal, so that's good. And then you're going to end in IDE. So for your non-metal part, you're going to lop off the end, like oxygen will become oxide, phosphorus will become phosphide, so IDE is the end. So I have an example here. I mentioned crisscross, so this is what I mean. So sodium is a 1A, so we'll put a +1. Sulfur is a 6A, so we'll put a -2. And what I mean to say is the number of sodiums I need is 2, and the number of sulfurs I need is 1. Okay, so the neutral formula is Na2S. Okay, and notice that we gave it the first name is the name of the metal, so Na is sodium, and then the last name instead of sulfur, it's sulfide. So be able to kind of do those. And then I'm not going to have you draw Lewis structures, but I'm going to have you interpret them. And I haven't decided how I'm going to do it yet. But for instance, if I was supposed to confirm the pot of valence electrons, what you do, remember, for valence electrons is look up the group number. So let's see, I'm going to kind of rewrite this. The number of carbons I have is 1, 2, 3, 4, 5. 5 carbons, C5, H, 1, 2, 3, 4, 5, H5. I have an oxygen, just 1, and I have a nitrogen, just 1. Now, assuming I got that right, let's come up with a pot of valence electrons here. With regard to the carbon, there are 5 of them, and it's a 4A element, so there are 4 valence electrons. With regard to hydrogen, there are 5 of those, and the number of valence electron is 1, so I get 5 electrons. With regard to oxygen, there's 1 of them, it's a 6A element. With regard to nitrogen, there's 1 nitrogen, it is a 5A element. So let's add these up. I got 25, 30, 36. So let's see if we have 36 electrons on our Lewis structure. So each time you see a dash, it's 2 electrons. So I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. Okay, now I'm going to do my lone pair electrons. 32, 34, 36. Okay, so that's what I mean about confirming that. Now, does each atom have a complete octet and octet, or in the case of a hydrogen, do it? And the answer is yes. You can kind of confirm that if you want. How many lone pairs of electrons are there? I'm liking 1, 2, 3. I just got 3 pairs of lone pair electrons. And again, I'm not sure how I'm going to do this, but it will be interpreting Lewis structures. All right, on to the next part. We talked about mixtures. So some what we call properties of mixtures is that each of the 2 or 3 or 4 or 5 or 6 things that are physically combined will keep or retain their original chemical properties. Another thing is the ratio of how you decide to mix the components can totally vary. It's up to the person who puts together the mixture. And then, though, as you change the ratio, then that's going to change. Let's see, properties of the mixture will change. Mixture can be separated back out into its components by physical means. Because they were physically tossed together, you can use some sort of physical means to separate them out. For example, evaporation is an example of a physical means. We talked about 2 types of mixtures. You guys told me this is a homogeneous mixture. You told me this is a heterogeneous mixture. Heterogeneous mixture is chunky. Okay. Homogeneous mixture is smooth. And then actually, as it turns out, solutions are types of homogeneous mixtures as long as they don't have any sludge at the bottom of them. In solutions, we have solution is equal to the solute, which is in lesser amount, plus the solvent, which is in greater amount. These two together make your solution. Anytime somebody says I have an aqueous solution, that means water is the solvent. We talked about these different types. Well, first off, we talked about solubility. We said that if you are going to mix a solute in a solvent, you can actually max out the amount of solute that you've dissolved. So I should say, if you get a sludge at the bottom, that means that you have maxed out. You have overrun your solubility. Okay, so we have these types of solutions. Unsaturated means that it could take more solute dissolved. Saturated means you've got a sludge at the bottom. Now, supersaturated means that you have somehow been tricky and basically dissolved more solute in a given amount of solvent than really ought to dissolve. Okay, so that's supersaturated. All right, chemical reactions. We said we use chemical equations to represent the chemical reactions, and we put reactants on the left side and products on the right side. We know that a chemical reaction has occurred if you have new substances are formed. Notice that during chemical reactions that we deal with, that actually all nuclei of the atoms remain unchanged, which means you have the same atoms of each type of element that you start with and end with. It's the same. Okay. So kind of know these. An S stands for solid in chemical equations, an L liquid, G gas, and AQ means aqueous. One of the things you're going to need to be able to do is to balance equations. And when we balance equations, we put a big number called a stoichiometric coefficient to the left of the species, the reactant, or the product. And when we do that, that big number applies to the entire unit. Remember, we've been talking about that. But when we get the same number of atoms of all of the different elements on both sides of the reaction arrow, we are actually just making sure that we're following the law of the conservation of matter. So this would be an example of one that we did. I don't know how to show you balancing equations, but I think, what did I say? I think I'm going to have one where you need to check to see is it balanced or not. Remember, we did aluminum, sulfur, oxygen, or actually you can keep SO4 together if you wanted to. Either way, Na, and you can do you can keep this oxygen go with this oxygen, or you can keep this together as OH and tally them up. And I don't think I'm going to do it right now, but let me know if you have any questions about that. So I think I'm going to, like I said, I'm not sure. I know that I'm going to have you balance equations, but I don't know if I'm just also going to have you look at equations and see if they're balanced or not. So is this equation balanced now? Or see, if we don't have any number to the left, that's assumed that it's just one. So you can see one methane, one O2, one CO2, and one H2O. And I think the point here is that if you count, for instance, little red balls, which represent oxygen atoms, no, we've got 2 here, and we've got 3 over here. So no, it's not balanced. It's also not balanced with regard to little white knobs, which is white atoms, which are hydrogens. So it's not balanced. Okay, so finishing up with a little bit of math. So the concept of a mole is very similar to kind of the concept of a dozen. If you have 1 mole of particles, you have 6.022 times 10 to the 23rd particles. I think I might have a question that the concept of a mole actually goes back to the element carbon is the standard. So if you have exactly 12 grams of this particular version of carbon, this particular isotope of carbon, then you have 6.022 times 10 to the 23rd carbon atoms. Excuse me. Okay, so any equivalency statement like this, 1 mole is equal to 6.022 times 10 to the 23rd. We'll go ahead and say atoms. We can use that as a ratio or a division ratio to work a problem. So for instance, it says, I'm not going to work it, I'll just set it up like we set it up in lecture. A sample contains 3.011 times 10 to the 23rd atoms. How many moles is that? So I would start with this number over 1. Don't forget the units. 3.011 times 10 to the 23rd atoms. And I want atoms to cancel, be left with moles. And that's where I go up to here, if I have this on my little cheat sheet, and then I can put 1 mole, 6.022 times 10 to the 23rd atoms. And then this one is different, isn't it? It says how many... Oh, this looks like how'd you guys let me get by with that? How many moles of carbon atoms are present in 5.45 times 10 to the 24th? It should be carbon atoms. Goodness gracious. So 5.45 times 10 to the 24th atoms over 1. So I want my atoms to cancel, so they're going to go in the bottom of the next term, and I want to be left with moles. And so here's where, again, the 1 mole goes on the top, and the 6.022 times 10 to the 23rd atoms goes on the bottom. Okay, all right. Okay, so this was the other one, and a lot of times when we're working physical science problems or chemistry problems, I'll just kind of look at that's going to be my first term, 2.5 moles, and I'm going to atoms, so I want moles to cancel. 1 mole and 6.022 times 10 to the 23rd atoms. And I bet this one's down here's the same too. So I put 0.00912 moles over 1. And again, 1 mole, 6.022 times 10 to the 23rd atoms. And that's it. Oh, last concept. Molar mass is the mass in grams of 1 mole. It's so cool. So grams per mole are the units for molar mass. And for the atoms, molar mass is the same number as the average atomic weight. And for compounds, the molar mass is the same number as the weight of the repeating unit, molecular weight or formula weight. So there will be a problem on the test, and it will look something like this. I'll pick an element. I think I'm going to do it for elements, not for compounds. But picking on silver, and I don't have my periodic table here. Drat, I can't believe that. So you would look up the molar mass of silver from the periodic table. I'm sorry, guys. And I would probably write that up here. So I would say 1 mole of Ag weighs or is equal to whatever that grams is. I'll put X grams of Ag, and that's from the periodic table. Periodic table. All right. So then what you're going to do is the first number is going to be 7.9 moles over 1. And can you see where I'm going to go ahead? I want moles to cancel, and I want to be left with grams of Ag. So I'm going to put 1 mole on the bottom, and I'm going to put whatever from the periodic table, this X grams that I got from the periodic table. So moles will cancel, be left with units of grams. Now for this one, we're going to look up on the periodic table. We're going to see 1 mole of Br is equal to X grams of Br, and that's from the P table, which you have one for your test, right? And then the first term is going to be that 0.0041 moles over 1. And I want moles to cancel. I want to be left with grams, okay? And so I'm going to put this 1 mole down here, and then this will be X. All right. One more type of problem dealing with molar mass. For helium, you'll look up on the periodic table, 1 mole of helium is equal to X grams from the P table. Now notice that to work this problem, I've got 5.6 grams of helium. I'll put that over 1. I want grams to cancel. I want to be left with moles. So in this case, I'm going to put 1 mole on the top, and I'm going to put that X grams from the periodic table on the bottom so that my units of grams will cancel. Okay. Look up the molar mass of lead. 1 mole of Pb is equal to X grams of Pb. This is from the periodic table. And then to work this problem, my first term is going to be 12.98 grams over 1. I want units of grams to cancel. I'm going to be left with units of moles. Put 1 mole on the top. Put that X grams in the bottom, and ta-da! You've got the answer. Okay? All right. So, the red cabbage. Did I just... Oh, yeah. Huh? Okay, so there will be some extra credit questions over the red cabbage. And I don't know if you recognize this, but this was for my, my Monday, Wednesday, Friday class. This is the whiteboard during lab. So a few things we talked about. People are familiar with acids and bases, okay? And then I'm going to throw in neutral. So what we do is we use the pH scale, a pH of it's generally from 1 to 14. So 1 would be most acidic, 7 would be neutral, and 14 would be base. And we said that actually anything between 7 and 14 is basic. And anything between 1 and 7 is acidic. And so kind of along those lines, the only thing that was neutral was a pH of 7. The other thing then is with regard to acidic, if something's acidic, it means has more H pluses. If something is basic, which we call the hydrogen ion, if something is basic, it has more OH minuses, which we call the hydroxide ion. Then I guess the other thing, and I don't think it's on your test, we talked about buffered solution. That the cool thing about a buffered solution is you can add acid or you can add base, and actually it has a base and an acid respectively to what we say neutralize the stuff that you add. But a buffered solution is stubborn to change its pH. It's buffered at a particular pH, and it fights pH change if you add acid or base. So I hope that was helpful, and let me know if you have any questions.